Imagine standing outside on a clear night, gazing up at the vast expanse of the universe. Each twinkling point of light represents a distant star, and each one tells a unique story. Some stars have burned brightly for billions of years, while others are just beginning their journey. The cosmos is a stage hosting a stunning array of stellar diversity, from the faint and humble red dwarfs to the magnificent and explosive supergiants. Today, we will embark on an exciting journey through this cosmic zoo, delving into the secrets behind the different types of stars that populate our universe. We'll explore their characteristics, sizes, colors, and how they fit into the grand narrative of stellar evolution. Each star contributes to the rich tapestry of the cosmos, and understanding them helps us appreciate the wonders of the universe even more. Now, let's spark your imagination with some astonishing facts. What if I told you that there are stars the size of cities, so small that they could fit in the palm of your hand? Picture that. And what about the colossal cosmic giants? These behemoths are so immense that if one were placed in our solar system in place of our Sun, it would engulf the orbit of Jupiter. Yes, the largest planet in our system. Get ready for a thrilling journey that will take us from the minuscule to the colossal, from freezing cold to unimaginable heat. The universe is full of surprises, and we're just getting started. If you're excited to learn more about the stars and their incredible stories, don't forget to like this video and subscribe to Exploring the Universe. Join us as we continue to uncover the mysteries of the cosmos. At its core, a star is a massive sphere of gas held together by gravity. These celestial bodies generate energy through a process known as nuclear fusion. Inside a star, the extreme pressure and temperature at its core allow hydrogen atoms to fuse into helium, releasing an immense amount of energy in the form of light and heat. This energy is what makes stars shine so brightly in the night sky, illuminating the darkness of space. The primary components of stars are hydrogen and helium. Hydrogen is the most abundant element in the universe and serves as the primary fuel for stars. As stars age and undergo various stages of their life cycle, they can fuse heavier elements, but hydrogen and helium remain the foundation of their composition. The balance between these elements, along with the energy produced from fusion, determines a star's characteristics, including its temperature, brightness, and lifespan. Stars can be classified based on several criteria: temperature, luminosity, mass, and stage of life. This is often measured in Kelvin, with hotter stars appearing blue and cooler stars appearing red. The temperature influences a star's color and overall characteristics. This refers to the total amount of energy a star emits per second. It can vary significantly from one star to another, even among stars of similar temperature. The mass of a star plays a crucial role in its evolution. More massive stars tend to burn hotter and faster, while less massive stars have longer lifespans. Stars progress through various stages, from formation in nebulae to their eventual death as white dwarfs, neutron stars, or black holes. The Hertzsprung-Russell diagram is a fundamental tool in astrophysics that visually represents the relationship between stars' luminosity and temperature. Developed independently by astronomer Ejnar Hertzsprung and physicist Henry Norris Russell in the early 20th century, this diagram has revolutionized our understanding of stellar evolution. Stars are plotted on the HR diagram based on their temperature, along the horizontal axis, and luminosity, along the vertical axis. This layout allows astronomers to easily identify patterns and categorize stars based on their physical properties and evolutionary stages. For example, most stars, including our Sun, fall along a diagonal band known as the main sequence, where they spend the majority of their life. Stars on the main sequence fuse hydrogen into helium at their cores and vary in size, color, and brightness depending on their mass. Main sequence. This is the most prominent region of the HR diagram, where stars spend most of their lives. It runs from the upper left, hot, luminous stars, to the lower right, cool, dim stars. Giants. Above the main sequence, this region contains larger stars that have exhausted the hydrogen in their cores and are now fusing heavier elements. These stars are significantly more luminous than main sequence stars. Supergiants. These are the most massive stars, located at the upper end of the HR diagram. Supergiants are incredibly luminous and have short lifespans due to their rapid consumption of nuclear fuel. White dwarfs. Found in the lower left corner of the diagram, white dwarfs are the remnants of stars that have shed their outer layers. They are small, dense, and gradually cool over time. By studying the HR diagram, astronomers can better understand the life cycle of stars, their evolution, and the physical processes that govern their behavior in the universe. If the HR diagram has your mind shining like a supernova, Why not give us a stellar like? Just as nuclear fusion powers the stars, your support fuels our journey through the cosmos. By liking this video, you're joining a community of star enthusiasts eager to explore the wonders of the universe together. Your engagement is a powerful form of social fusion, bringing us closer to discovering the secrets of the stars. Red dwarfs are the smallest and coolest type of stars in the universe. They typically have a mass ranging from about 0.08 to 0.6 times that of our Sun, which gives them a distinctly lower luminosity. Their surface temperatures are relatively low, usually between 2,500 to 4,000 Kelvin, resulting in a reddish hue that sets them apart from brighter, hotter stars. Despite their modest appearance, red dwarfs are incredibly efficient at burning hydrogen. This efficiency allows them to sustain nuclear fusion for an astonishingly long time, making them the most abundant type of star in our galaxy. The closest star to our solar system is Proxima Centauri, a red dwarf located just over 4 light-years away in the Alpha Centauri star system. Proxima Centauri has a mass of about 12% that of the Sun and a surface temperature of around 3,050 Kelvin. Though it is not visible to the naked eye, Proxima Centauri plays a crucial role in discussions about exoplanets and the search for extraterrestrial life, as it hosts at least one confirmed Earth-sized planet within its habitable zone. One of the most remarkable features of red dwarfs is their incredible longevity. Unlike larger stars that burn through their fuel quickly and have relatively short lifespans, red dwarfs can live for trillions of years. This means that, theoretically, they could outlive billions of other stars, including our own Sun. This extreme lifespan is due to their slow rate of nuclear fusion. While larger stars might shine brightly for a few million years, red dwarfs can remain stable and luminous for tens to even hundreds of trillions of years. As the universe evolves, these modest stars will continue to light up the cosmic stage long after more massive stars have burned out. Red dwarfs are fascinating celestial bodies that, despite their small size and low luminosity, hold significant importance in our understanding of stellar evolution and the potential for life elsewhere in the universe. Dr. Luis Estrella, an astrophysicist from the Federal University of Rio Grande do Sul, emphasizes the significance of red dwarfs in our understanding of the universe. He states, "Red dwarfs are the most common stars in the universe. Their longevity makes them excellent candidates in the search for habitable planets and potential extraterrestrial life." Stars similar to our Sun are classified as G-type main sequence stars, or G-dwarfs. These stars are characterized by their medium size and yellow hue, with surface temperatures ranging from about 5,300 to 6,000 Kelvin. They possess a mass approximately 0.8 to 1.2 times that of the Sun and have a moderate luminosity, which allows them to maintain a stable environment over billions of years. G-type stars, including our Sun, play a crucial role in the Hertzsprung-Russell diagram, occupying a significant portion of the main sequence. This category of stars is vital for understanding stellar evolution and the life cycles of other types of stars. Being in the main sequence means these stars are in a stable phase of hydrogen fusion, where they convert hydrogen into helium at their cores. This process generates the energy that powers the star and provides the necessary conditions for the development of life on surrounding planets. As G-type stars age, they undergo a transformation that leads to their eventual demise. After exhausting the hydrogen fuel in their cores, they will expand into red giants, a stage during which their outer layers will swell and engulf nearby planets, potentially including Earth. This dramatic change results in the star shedding its outer layers, creating a stunning planetary nebula. The core that remains will eventually cool and shrink into what is known as a white dwarf, a dense, hot remnant that will gradually fade over billions of years. This transformation not only concludes the life cycle of stars like our Sun, but also contributes to the chemical enrichment of the galaxy, as the elements produced during their lifetimes are released into space, nurturing the formation of new stars and planets. Red giants are the next stage in the life cycle of stars like our Sun. When a star exhausts its hydrogen fuel in the core, it can no longer support the nuclear fusion process that keeps it stable. As hydrogen is depleted, the core contracts under gravity, causing an increase in temperature. This heat allows helium, which has accumulated in the core from hydrogen fusion, to begin fusing into heavier elements like carbon and oxygen. As the core contracts, the outer layers of the star expand dramatically, transforming the star into a red giant. This process marks a significant change in the star's structure and energy output, leading to the star becoming much larger than it was during its main sequence phase. Red giants are characterized by their large size and lower surface temperatures compared to their main sequence counterparts. While their cores are extremely hot, often exceeding 100 million Kelvin, their outer layers cool down, resulting in a reddish appearance. These stars can be hundreds to over 1,000 times larger than our Sun and are incredibly luminous, emitting vast amounts of energy. Despite their lower surface temperature, the sheer size of red giants allows them to shine brightly in the night sky. A prominent example of a red giant is Aldebaran, located in the constellation Taurus. Aldebaran is approximately 44 times the diameter of the Sun and has a surface temperature of about 3,900 Kelvin. It is often referred to as the Eye of the Bull in its constellation and is one of the brightest stars in the night sky. Its luminosity is about 1,500 times greater than that of the Sun, making it a striking feature of the celestial landscape. Supergiants are among the largest and most luminous stars in the universe. These colossal stars can have masses ranging from 10 to over 100 times that of the Sun, and they are characterized by their extraordinary brightness and immense size. Supergiants are typically classified into two main categories based on their temperature: blue supergiants and red supergiants. Blue supergiants. These stars are hotter, with surface temperatures exceeding 20,000 Kelvin, giving them a blue appearance. They burn through their nuclear fuel at an extremely rapid rate, resulting in a relatively short lifespan, often just a few million years. Red supergiants. These stars have cooler surface temperatures, ranging from about 3,000 to 4,000 Kelvin, which gives them a red color. They are also massive but may have longer lifespans than blue supergiants, lasting several million years before exhausting their nuclear fuel. Two well-known examples of supergiants are Betelgeuse and Rigel, both located in the constellation Orion. Betelgeuse. This red supergiant is one of the largest stars visible to the naked eye. It has a diameter about 1,000 times that of the Sun and is approximately 700 light-years away from Earth. Betelgeuse is nearing the end of its life cycle and will eventually explode as a supernova, leaving behind a neutron star or black hole. Rigel. In contrast, Rigel is a blue supergiant that is one of the brightest stars in the night sky. It has a mass about 20 times that of the Sun and shines with a luminosity around 120,000 times greater than our Sun. Rigel's temperature is around 11,000 Kelvin, contributing to its blue color and extreme brightness. Like Betelgeuse, Rigel will also face a dramatic end, likely culminating in a supernova explosion. White dwarfs represent the final evolutionary stage of medium-sized stars, like our Sun, after they have exhausted their nuclear fuel. As a star reaches the end of its hydrogen-burning phase, it undergoes significant changes. The core contracts and heats up, while the outer layers expand and are eventually ejected into space, forming a planetary nebula. What remains is the hot core, which becomes the white dwarf. This remnant is composed primarily of carbon and oxygen, formed from the fusion processes that occurred during the star's earlier life stages. Unlike more massive stars that may explode as supernovae, medium-sized stars end their lives more quietly, leaving behind a white dwarf. White dwarfs are characterized by their small size and incredible density. Typically, they are about the size of Earth, but they contain a mass comparable to that of the Sun. This means that white dwarfs have an extraordinarily high density, with a single teaspoon of white dwarf material weighing several tons. As they no longer engage in nuclear fusion, white dwarfs gradually cool over billions of years. Initially, they are extremely hot, shining brightly, but over time, they lose energy and fade, eventually becoming cold, dark remnants known as black dwarfs, though the universe is not old enough for any black dwarfs to exist yet. A notable example of a white dwarf is Sirius B, which is part of the Sirius star system, along with its brighter companion, Sirius A. Sirius B is about 10 times more massive than Earth but has a radius similar to that of our planet. Originally, it was a much larger star that underwent the typical life cycle, shedding its outer layers and leaving behind the dense core. Sirius B is an important object of study in astrophysics due to its proximity and the insights it provides into stellar evolution. Neutron stars are formed from the remnants of massive stars that have undergone a supernova explosion. When a massive star, typically over 8 times the mass of the Sun, exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core collapses under its own gravity, causing protons and electrons to combine and form neutrons. This process results in a neutron star, which is incredibly dense, so much so that a sugar cube-sized amount of neutron star material would weigh about the same as a mountain on Earth. The outer layers of the star are expelled in the supernova explosion, while the core remains as a neutron star. Neutron stars are characterized by their extreme density and small size, typically measuring about 20 kilometers in diameter. They possess incredibly strong gravitational fields and can rotate at astonishing speeds, completing a full rotation in just a few milliseconds. The rapid rotation of neutron stars, combined with their strong magnetic fields, can lead to the emission of beams of radiation from their magnetic poles. If these beams sweep past Earth, they can be detected as regular pulses of radiation, which is why spinning neutron stars are known as pulsars. Pulsars. These are a type of neutron star that emits beams of electromagnetic radiation. As the star rotates, the beams are directed outwards, resembling a lighthouse effect. Pulsars can spin very rapidly, with some completing hundreds of rotations per second. Magnetars, a subclass of neutron stars with extremely powerful magnetic fields. Magnetars can produce intense bursts of X-rays and gamma rays. These magnetic fields are so strong that they can affect the behavior of matter in their vicinity and are thought to be responsible for the energetic phenomena associated with magnetars. Stellar black holes are formed from the remnants of massive stars that have reached the end of their life cycles. When a star with a mass greater than approximately 8 times that of the Sun exhausts its nuclear fuel, it undergoes a catastrophic collapse during a supernova explosion. The core of the star collapses under the force of gravity, compressing matter to an extent where it forms a singularity, a point of infinite density. As the core collapses, the gravitational pull becomes incredibly strong, creating a region known as the event horizon. This is the boundary beyond which nothing can escape the gravitational grasp of the black hole, not even light. Because light cannot escape, black holes are invisible and can only be detected by observing their effects on surrounding matter. Black holes are characterized by their extreme gravitational fields and the event horizon that marks the point of no return. The gravitational pull of a black hole is so intense that it warps spacetime around it, leading to fascinating effects like gravitational lensing, where light from distant stars is bent around the black hole. Stellar black holes, formed from the collapse of massive stars, with masses ranging from about 3 to several tens of solar masses. Supermassive black holes. Found at the centers of galaxies, these black holes can have masses ranging from millions to billions of solar masses. Their formation is still a subject of research, but they may arise from the merging of smaller black holes or the accumulation of mass over time. Intermediate black holes. These are hypothesized to exist with masses between stellar and supermassive black holes, though they are more elusive and harder to detect. Black holes cannot be observed directly due to their nature, but their presence can be inferred through various methods. Effects on surrounding matter. When a black hole pulls in nearby stars or gas, this material forms an accretion disk as it spirals in. The friction and heat generated in the disk cause it to emit X-rays, which can be detected by telescopes. The collision and merger of black holes create ripples in spacetime known as gravitational waves. These waves can be detected by observatories such as Laser Interferometer Gravitational Wave Observatory, providing a new way to study black holes and their properties. The life cycle of a star is a complex journey that begins in the depths of nebulae and culminates in various endpoints based on the star's initial mass. Here's an overview of the stages in the stellar life cycle. Stars begin their lives in nebulae, which are vast clouds of gas and dust in space. Under the influence of gravity, portions of these clouds begin to collapse, forming dense regions known as protostars. As the protostar contracts, it heats up due to gravitational energy being converted into thermal energy. When the temperature and pressure in the core become sufficient, nuclear fusion ignites, and the protostar becomes a main sequence star. The main sequence is the longest phase in a star's life, during which it fuses hydrogen into helium in its core. This phase can last billions of years, depending on the star's mass. Low-mass stars. Stars like red dwarfs spend a significant portion of their lives in this phase, often for trillions of years due to their slow fusion rates. Medium-mass stars. Stars like our Sun have a lifespan of about 10 billion years in this phase. High-mass stars. Massive stars burn through their hydrogen quickly, living for only a few million years. The fate of a star is largely determined by its mass at birth. Low-mass stars. After exhausting their hydrogen, low-mass stars swell into red giants and eventually shed their outer layers, creating planetary nebulae. The remaining core becomes a white dwarf, which will gradually cool and fade over billions of years. Medium-mass stars. Similar to low-mass stars, they will expand into red giants. After shedding their outer layers, they too will leave behind a white dwarf. High-mass stars. These stars undergo more complex processes, eventually exploding as supernovae. The core left behind may become a neutron star or, if massive enough, collapse into a stellar black hole. The diversity of stars plays a crucial role in the formation of chemical elements in the universe. During their lifetimes, stars undergo nuclear fusion, which transforms lighter elements into heavier ones. For instance, hydrogen is fused into helium in main sequence stars, while in more massive stars, Fusion continues to create elements such as carbon, oxygen, and iron. When these massive stars reach the end of their lives, they explode in supernovae, scattering these newly formed elements across the universe. This process enriches the interstellar medium with essential building blocks for planets and life, contributing to the overall chemical complexity of the cosmos. Without the diverse range of stellar types, the elements necessary for life as we know it would not exist. Thus, the life cycles of different stars are integral to the ongoing chemical evolution of the universe. Stellar diversity significantly influences the formation and evolution of galaxies. Different types of stars contribute to the dynamic processes that shape galaxies over time. For example, massive stars, which burn brightly and die quickly, can trigger star formation in nearby regions through their explosive deaths. Conversely, the remnants of low-mass stars contribute to the gradual evolution of galaxies by providing a steady supply of lighter elements. Moreover, the interactions between stars and their environments, such as supernova explosions, stellar winds, and gravitational interactions, help determine the structure and dynamics of galaxies. The presence of different stellar populations can influence the rate of star formation and the overall morphology of a galaxy, leading to the rich diversity of galaxy types we observe in the universe today. Studying stellar diversity provides valuable insights into the history and future of the universe. By examining the characteristics of different stars, astronomers can trace the evolution of galaxies and the processes that have shaped the cosmos over billions of years. For instance, the distribution of various star types within a galaxy can reveal its age and the history of star formation within it. Additionally, understanding the life cycles of stars helps predict how galaxies will evolve in the future. As stars continue to form, evolve, and die, they will shape the universe in ways we are only beginning to comprehend. Stars serve as cosmic laboratories of extreme physics, where the fundamental forces of nature play out on a grand scale. Through the processes of nuclear fusion, gravitational collapse, and explosive supernovae, stars exhibit phenomena that challenge our understanding of physics and the universe itself. Moreover, our connection to stars is profound. We are literally made of star dust. The elements that constitute our bodies were forged in the hearts of stars long ago, linking us to the cosmos in a very tangible way. This relationship underscores the importance of studying stars, as it enhances our understanding of our own origins and place in the universe. Studying stars is key to unlocking the mysteries of the cosmos. They hold the secrets of our existence, the history of the universe, and the potential for future discoveries. By continuing to explore the stars, we deepen our understanding of the universe and our connection to it. If this video has sparked your curiosity as brightly as a blue supergiant, don't forget to subscribe to Exploring the Universe. Together, we will continue our journey through the diverse celestial bodies that illuminate our universe, uncovering the wonders that lie beyond our world. Join us for more adventures in the cosmos.